Hello, I'm Kirsch, Senior Electrical and Electronics Design Engineer, former adjunct professor specializing in hardware and power electronics. In this video, I'm going to show you a technique that you can use to stress test thousands of boards before they even hit your test bench. How is that possible? Well, we'll be using the power of PSpice under the Allegro X platform. And what this does, I'm going to show you how you can stress test those little tolerances for each and every single one of your components in a design, right? Using computer simulation. That is the power of PSpice. This way, if you have some components that are 20% off here and there, 10% off here and over there, you know which components are going to send you in all the way to the left kind of operation to all the way to the right operation, so you can find those corner cases that are going to be nasty surprises should you produce these out on the field. Okay, so without further ado, I'm going to show you how to do that in PSpice. So I'm going to be demonstrating this using a flyback converter. This is a power electronic circuit, and every component in here has some like significant effect that can blow this thing up actually. But the most important components in this design are the transformer, most definitely. So if you're familiar with that, it's the transformer and the inductance in that transformer. There's also this resistor right here in this CS pin, okay, for this sensing of the circuit. You also have your sense resistor and your feedback circuit right here. These two resistors, got to be mindful of these. Now, there are other components in here like your compensator capacitor, your compensator network circuit with the resistor as well, the LED resistor that gets pulled up, and anything that can affect the compensation circuit, anything that can affect the snubber circuit, okay? We need to be aware of those components and their tolerances and how they can vary as well. Now, what you can do is only set specific components to have their tolerances affected, but I had to do everything. I went overboard. I did all of them. So let me show you this. I'm going to select all of my components with a Control A and then Control E, and then go into my parts list. Here I have all of my parts, my capacitors, my resistors, and if I scroll down to tol, that's my tolerance. This is the field value that's going to be varied and adjusted in my simulation. Okay, so what my simulation is going to do is test a bunch of these tolerances at different random points. So it may have my C snubber capacitor be 10% greater than it's supposed to be, or 10% less than it's supposed to be in terms of capacitance, along with keeping the rest of the circuit same. It's going to use a random set of numbers in random combinations to test realistic scenarios, just like you would experience on a real printed circuit board. Okay, so if we go into our simulation profile, let's see how I set this up. With the regular time domain, I check marked this Monte Carlo / worst case scenario. I went with Monte Carlo, not necessarily worst case. That would be a different situation. And we have enable PSpice AA support and legacy in case you need that. How many runs am I going to want to do? Anywhere from 20 to 30 runs, right? I decided to go with 20 because it's shorter. And then what distribution do I want? A uniform distribution, Gaussian, random number seed as well, to say maybe I want a specific random number seed to test what my board performance and board production volume and variance is going to be like. I can save the data from all of my simulations if I want to. So that's what I had set, and everything else I left the same. There are other settings where you could fill in specific Monte Carlo analysis tests, but this is fine. So you go with apply and OK, and then I ran the simulation. Now I decided to run all of the components under the stress test. Okay, so this took me a little while. Took about 30 to 45 minutes for the simulation to run. Be mindful of that. You may need to hit run, walk away, go do some other tasks, and come back to it. All right, let's see what the results say. And here we go. So, wow. We can see here that there are no specific random set of boards that are going to have our design blow up or anything. So basically what we wanted to look at here, right, is what's the distribution of performance? The distribution of performance. We see that, yeah, they're going to have some drift in their performance, but for the most part, we're not going to be having boards that are operating at 3 volts or something crazy like that, or just operating outside of normal expectations. For considering, if we had, say, 500 boards, 1,000 boards, reasonable operation. That's why we do this Monte Carlo analysis stress test. So I'm going to zoom in. Now, what this means is we are not seeing necessarily for the worst case. We're not checking for the worst case. We're checking for across most cases for reasonable variation. And then as we're zoomed in here, look at the performance in general. Pretty much most of our designs are not going to have much ringing at all. The voltage on the output is going to hover around at most 5 volts, on average 5.2 volts, and at the very least, somewhere around 5 volts. So that's great. That is great performance. And in general, most of the PCBs should not be pulling or drawing more than 5 amps through the diode. All right, so we have assessed what is our average behavior amongst all our boards in most cases, and the performance looks fine to me. Now, what about a worst case scenario? A corner case, because we do have those corner cases. We need to find out and test still, what if we just get a board that has all resistors that are 20% or 10% higher than they're supposed to be, or all capacitors that are 20% lower than they're supposed to be? What's going to cause this board to break and perform just out of character? I'm going to show you how to test and analyze that in the next section. So in the design to test for worst case behavior, go to the PSpice settings, then you'll check your time domain transient, and then here click on the Monte Carlo / worst case sensitivity analysis. Okay, worst case / sensitivity analysis. And with these settings, maybe 20 runs and both DEV and LOT, it just depends on your situation. I kept it the same. Once you click apply, then okay, it's going to run multiple simulations to see what's going to give you the worst case scenario. And also very important to include that output variable, say the voltage around a specific element, i.e. the voltage for our load. And you need to use that correct term, okay, for that variable. Otherwise, it's not going to recognize what you're talking about. Once that's done, you hit run, and then you see the results. And look at this. I ran my simulation and check out my worst case scenario. It seems that around 8 milliseconds, there is a situation where my voltage is going to, it stays steady at 5 volts and whatnot. But in 2 cases, it will suddenly jitter, okay, and shake around that 5 volt mark and then restabilize, yes. And here we've got the current right around here. It'll suddenly do a jerk. This shows us what kind of behavior we can expect to see in a worst case scenario. And you have your resistors, capacitors at certain values that are pushed to the limit or within a specific values or ranges, then you can get this odd behavior in 2 circumstances. What I would do is go ahead and go to File, Save As to save that result so that this can be analyzed later. So I've renamed this file to worst case, V drain, V out, I drain, hit save, and then that saves that simulation data. Now, why does all of this matter again? See, your bench prototype uses normal, typical values for your components. But when your board goes to production, the production uses the full spread of components. And if, say, 3 out of 30 of your boards fail or perform outside of what's expected normal operation, that is a 10% failure rate. Let's say I were to vary my MOSFET, like if my MOSFET were to vary its peak drain voltage that it can handle from 52 volts to 60 volts. That's only a 13% margin. That's not much room to work with. So I'd consider upgrading my MOSFET from, say, a 60 or 70 volt MOSFET to an 80 to 100 volt MOSFET to give myself more headroom for that variation in operation, right? I'll give you another example. Consider the snubber circuit. What if I discover that my resistor in that circuit, it can vary anywhere from needing to absorb 1 watt of power to 1.5, maybe even 2 watts of power. Instead of looking for most of my resistors being, say, 1.5 watts, I may want to rate that resistor at 3 watts instead of 1.5, just to cover that distribution. Another example, let's say my feedback resistors are giving me a tolerance of about 5% or 250 millivolts of drift, so to speak. Then I might start considering and say, hey, that is too much variation. We need to look at buying 1% tolerance resistors instead of 10% tolerance resistors. And that's Monte Carlo analysis, testing production variance before you build anything. So before you send out anything into production, do that Monte Carlo analysis to get an average performance of your boards and make sure their performance is acceptable. Thanks for watching this video, and I will see you in the next one.